I'm just going to make a quick video on a concept that I tend to confuse with each other a lot. So I'm just gonna make a quick video which I can see in the future if future me gets confused by it, because this is something that definitely comes at least in an MCQ, and it definitely has come in mains as well, and I fucked up that question. Um, so yeah, I'll just get right into it. It's in dual nature of radiation and matter, and I got it cleared by NCRT. I'm not sure if the entire explanation of what I'm giving is correct, but it gives me conceptual understanding. So shut the fuck up, right? This is basically about how the effect, like how a different characteristic of light is affecting the photocurrent, right? So the first one, that is the easiest one, is the intensity of light. Intensity of light. If you increase the intensity of light, there are more electrons, like it was observed in the experimental setup. The photocurrent is increasing. What is happening over here is when you're increasing the intensity of light, there are more electrons being ejected. They'll have the energy won't be changed by the intensity of light. That is not being touched at all by intensity. All it's doing is it's deciding how many electrons are being ejected, how many photoelectrons are being formed. Now, after the intensity, so what you're doing is if you increase the intensity of light, there's a higher photocurrent, which means that there are more electrons being ejected. And if it is if it is a lesser intensity, then lesser electrons are being ejected. Pretty obvious, pretty simple to get. Now, this is where I usually tend to get confused, which is in the stopping potential. How the potential is affecting the photocurrent. So it was seen. I'll just make a very raw, quick diagram. What the So this is collector plate. This is emitter plate. This is the source, which is sending in the radiation so that this can emit electrons and the collector can collect the electrons. And this circuit is there, which has a commutator, etc., whatever. But that's not important to what we're doing right now. It was in this, what they did was they messed around with the potential of the collector plate. So first what they did was they increased the positive potential of the collector plate. So this is called accelerating potential. So what they did was and this is you have to check it only for a fixed frequency of the incident radiation. This incident radiation should be a fixed frequency. If you're changing around with the intensities of the radiation, that doesn't matter. As long as there's a fixed frequency, then it's fine, because this potential will be dependent on the frequency of the light, that we'll see in the next point. So what is happening over here is electrons are being emitted from here. Electron is coming. All the electrons don't have the same energy. Each electron can have different kinetic energy. So it's being emitted towards the collector plate. So what is happening is, if you first of all, I'll just tell you the observation. So if when you increase the potential, the photocurrent was increasing, but the photocurrent was increasing only to a certain maxima point. So that maxima point is called the saturation current, and at this point what is happening is all the electrons from emitter plate are reaching the collector plate. All of them, not a single one is left behind. At that point, that current is called saturation current. So what is happening here is an electron is coming, and what you've done is you've increased the potential, so it's able to reach it. Now what they did was they went backwards. They changed the polarity. They reversed the polarity. they started decreasing this and going towards a negative potential. So electrons started getting repelled. So light is coming here, it's ejecting electrons, they're coming with some kinetic energy. The more energy and more energetic ones are making it to the collector plate, the lesser energetic ones are being sent back. They're being sent back, they're not able to make it, they don't have enough kinetic energy to make it to the collector plate. Now you decrease it more, it becomes more and more negative. The repulsion becomes so strong that at one point even the maximum possible kinetic energy of the electron is not able to reach it. At this point, the potential that is of the collector plate is called a cutoff potential or stopping potential. It's mathematically represented as K max is equal to stopping potential. Stopping potential as in EV naught. Obviously, I'm once again stressing and emphasizing on the point that this is the stopping potential is dependent on the frequency of the light. It's not dependent on the intensity. Now I'll show it here with a graph. That is not dependent. This is the photocurrent. This is potential. Here it's accelerating, here it's retarding potential. So now if you take different intensities of light, the confusion that arises for me is that there'll be some sort of change somewhere, but that doesn't happen. When you take different intensities of light, so first I'll draw the basic how it works. So this is stopping potential. It increases, photocurrent is increasing and it reaches a point where it saturates. This is the saturation current and this is the stopping potential, because when the photocurrent is becoming zero, when you decrease the potential that much, it's become that much negative. So now I'll do it with different intensities of light but the same frequency of light. It will come like this. These represent different intensities of light with the same frequency of light. That is further explained by the third effect. So first we can explain why the saturation current is at different points. This is because of intensity. So we've seen that intensity decides how many electrons are being ejected. It doesn't decide the energy of each individual electron, it just decides how many are being ejected. So you can see over here, this is the higher intensity because the photocurrent is higher. More electrons are being ejected, so its photocurrent is higher. Now this is the second one and this is the least intensity out of all of these three. That is pretty clear. But now we check that the stopping potential of all of these is the same point, and that is because the frequency of the light has been taken constant. Now we'll explain it with third point why it stays constant over here. So I'll let the graph stay because it's useful. The third is the frequency of the light. So we know that frequency decides energy. Frequency is involved in the energy formula, and it's directly involved. So if you take a higher frequency light, higher kinetic energy will be imparted to the electrons. So what the frequency is doing is it's controlling the energy of each individual electron. So if you take a higher frequency, there's a higher kinetic energy and the maximum kinetic energy will also be higher. So it's directly controlling the stopping potential. You can see from here. So if the frequency of the light stays the same, the energy, the K max of the light will stay the same. And if it's different intensity or same intensity, that doesn't matter, because the energy is of each electron is staying the same. The kinetic K max is staying the same. So if K max is staying the same, stopping potential will automatically be the same. Now I'll rub this little bit. Now what we have done, now what we've done is we've taken light of same intensity but different frequencies. Again, frequency is controlling energy, intensity is controlling how many electrons are being ejected. So frequency, so for different frequency, this kind of graph will come. We can see here, this is the least stopping potential, this is more stopping potential. Magnitude wise, this is the least, this is more, this is more stopping potential. So we can see also the reason we have taken the same intensity of light is so that the saturation current of all three will be the same, obviously. So now the stopping potential is different and we can assign the frequencies for this. Say we have taken F1, F2, F3. This is for F1 frequency, this one is for F2, then this is for F3. Now we can see that since the frequency of the light is controlling the energy, maximum kinetic energy of an electron, we can see that if there is a higher frequency, there is a higher frequency of light, there's a higher Ke max, which means that if the Ke max is more, you need more stopping potential to stop it from reaching to the collector plate. So we can see over here, F3 has the least stopping potential. So that means the lesser stopping potential is required to stop an electron. So that means the maximum possible kinetic energy of that electron will be lesser compared to others. So then F3 is lesser than F2 and then it's lesser than F1. That makes it pretty obvious. To sum it up clearly, intensity is deciding the number of electrons ejected. Frequency deciding the Ke max, and this Ke max is deciding the stopping potential. This is all interconnected. I don't think I should be confused with it now, but in case I get confused with it, which I don't think I should, this video is there to help me in the future. This is sort of like a time capsule, a message to the future version of me that you're fucking stupid, you dumb prick. And this is a very easy explanation. I don't understand why you didn't get it, but now you will. Pretty easy.